Good evening and welcome to you all, a warm welcome to the inaugural lecture in SLAC's public lecture series. I'm thrilled to see so many people here, to see that you're all interested to know what goes on here at SLAC, and I hope that you'll find this evening's investment well worth your time. My name is Jonathan Dorfin. I'm the director of the laboratory. SLAC is funded by the Department of Energy out of Washington. It is funded under a contract with Stanford University. University runs the laboratory for the Department of Energy. Therefore, SLAC is a full and integral part of the university here at Stanford. As befits an academic institution and a university, all the research which is conducted here at SLAC is entirely in the public domain. We don't do anything here that is classified or in any way protected from the public domain. So if people want to do experiments at the laboratory, they're proposed and they're reviewed, peer-reviewed in a public and open way. And then all of the data and all of the technical innovation and all the technical advances that are made are then published in open public journals. There are about 3,000 researchers from 25 different nations that take advantage of the facilities here at SLAC. So we're not just a national laboratory, but indeed we're a host to an international community. And for those of you who live in the community, I just want to thank you, because the users who come here, do their research, spend from a few days to a few weeks to, in some cases, a few years, feel very welcome by our neighbors and appreciate greatly how we welcome them into the community, and I want to just thank you for that. This evening, it's my pleasure to introduce Neil Calder, who will give the first of these lectures. And Neil is head of the communications department here at the laboratory. Communications department handles internal communications, it handles external communications, government relations, public relations, outreach, all aspects of communicating both within and without the laboratory. We were most fortunate 2 years ago to snag Neil away from a similar job which he had for a very large laboratory called CERN in Geneva. And we're able to bring him and his family here, and we've been very grateful that Neil was able to come here. So I hope you'll enjoy the lecture, and I hope you will find it interesting enough to want to come back and engage us in the series. Thank you, and welcome, Neil.
Well, good evening. It's a great pleasure for me to look out in this room, which is absolutely full, because I've been preparing this talk for a couple of weeks and wondering, would anybody actually come and listen to it? Which has been a little bit of a depressing process, so I'm delighted to see you. Welcome all here. What I'm going to do tonight is give just a very, very gentle brushstroke over what happens here at SLAC. SLAC, the Stanford Linear Accelerator Center. I'm going to talk about particle physics that is done here. I'm going to talk about synchrotron radiation research that's done here, and also something to do with particle astrophysics and cosmology. All of these terms, don't worry about. We'll get into them more during the talk. Jonathan was very kind to say that SLAC snatched me away from CERN in Geneva. I'd just like to say that it's been a great honor for me to be here at SLAC, because though you may not know it here in Palo Alto, Menlo Park, SLAC has an international reputation all around the world. Anywhere that physics is discussed, on street corners around the world, in pubs, in bars. The name SLAC has a very special resonance, because SLAC, right from the beginning, really, of particle physics, high-energy physics, has led, has been innovative, has been groundbreaking in many, many different ways. And for me, it's wonderful to be here, and also the weather's better, and the wine's also very good. So I'm delighted. So we'll start off. So you can see here a little bit of geography. That this is 280 going along here. These are mountains. Over behind the mountains, you probably know there's an ocean. And beyond there, there's Asia, but we'll concentrate on this at the moment. You can see Sandhill Road going down here, and this is our laboratory here. This is what we could call the sort of business end. This is where we do the research. These are office buildings where we do sort of office type things, and you are here in this building here. And here we have a range of laboratories, workshops, which all contribute to the work we're doing here at SLAC. This building here is our linear accelerator. SLAC was, building of SLAC started in about 63. We were complete in 66. We're nearly 40 years old. There's been research going on here. And this linear accelerator has been the backbone of the research at this lab during this whole period. It really is the most amazing piece of equipment that in my house I have nothing technological which is 40 years old, which still works. And yet this thing is not only working, but has increasingly got better and better with time, which again is a pretty rare event. It is also the longest building in the world. Well, I say it's the longest building in the world, and nobody yet has contradicted me. Does anybody know what the second longest building in the world is? The Great Wall of China. No, that's not really a building, that's a wall. Doesn't qualify. The Space Shuttle building. I haven't heard that. Maybe. What I do know is the Hong Kong airport terminal, which is exactly 6 yards shorter than I'm sure, had they known, they would have added a little shed on the side to make it better. So anyway, this is what it looks like on the surface. However, this is a more important view of our lab, because here you see what is hidden, which is the various accelerated structures, most of which are underground. You can see the 2-mile-long linear accelerator. At the end of the linear accelerator, you can see circular rings, 1 and 2. I'd like you to ignore this one, the sort of flatter one at the moment, because we're not using it. But maybe we will later, but we're not using it at the moment. And we'll concentrate today in our talk on this one here. Also, you can see on this chart another smaller accelerator here. You'll notice by looking at this that this is a land of acronyms. We don't use language. We use SLAC, PEP, SPEAR, SSRL. And I'll try and explain these acronyms to you as I go along. Here is our research yard, a smaller accelerator. Sandhill Road, very important over here, is Safeway, which I spend a lot of my time in. And in fact, even more important is this is where my wife and I live at the moment. And just out of publicity, we'll be opening our house to the public next weekend for a small fee so we can pay the rent. So anybody wants to come through, pleased to see you. I'm going to talk now about particle physics to start off with. Later on, I'll get on to synchrotron radiation and cosmology, but this bit of it is really about particle physics. What we do is get a particle, which is called an electron. We start it off here, and we whiz it down the 2-mile-long accelerator. More or less the same time, or a little bit later, we get a different particle, which is called a positron, which is the antimatter version of the electron. And we'll come back to that. And we shoot that one down the linear accelerator, 2 miles long. The electron goes down and then goes around one of the arcs of this ring. At more or less exactly the same time, the positron goes around the other arc of the ring. So they go round, and what we hope is right here, they actually collide. They smash into each other. And it is the study of these collisions which is the basis of the particle physics that we do here at SLAC. These particles, when they're going down the accelerator, are in fact traveling about as close to the speed of light as we're ever going to get. They go at 99.99999999999. I'll keep going until you get bored. Lots of nines, very, very, very close to the speed of light. And it's difficult to get a concept of how fast the speed of light is. So I did a little calculation. But this is 2 miles down here. By the time you've gone around to the collision area, it's something like 2 3/4 miles. Now, if you get somebody up here with a rifle and you shoot off the electron at exactly the same time he pulls the trigger of the rifle, by the time the electron has gone zoom around and is actually meeting its fate here, the bullet is still in the barrel of the rifle. It hasn't left the barrel of the rifle. So these things are going really, 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 really fast. In fact, I cannot conceive in any way at all of how fast these are going. And this is one of the interesting things about particle physics, the work we do here. Nearly everything we do goes beyond our range of normal sensitivity. That you can't see particles, you can't hear them, you can't touch them, you can't, what other senses? You can't taste them. Everything happens at a level which is beyond our normal sensitivity. But the fact that our amazing staff, the technical staff, the engineers, the physicists, can control and organize these experiments so successfully continues to absolutely amaze me. Here's another pretty view of the longest building in the world. Here is 280 at night, headlights of the cars. Incidentally, this building was built before they built 280, and so they built the bridge all by itself, where it stood for a long time looking very lonely, over our accelerator, and then they finally built their motorway after this. I don't know what these people are doing here, but I assure you it's strictly legal. It may look suspicious, but it's not. The accelerator itself is underground. It is under the building you've just seen, about 20 feet under the ground. And this is what it looks like inside. It's actually quite rare to get inside because this accelerator, we keep it running as much as we possibly can. It runs 24/7 for about 9 months of the year. And when it's running, we don't go down and inside it. So this is what it actually looks like. It's a long, long, long straight tunnel. The actual business goes on in here. This tube here is the actual accelerator tube. Inside the tube, there is a very small little vacuum chamber about this size, which of course is totally, totally evacuated. It's got a very, very high vacuum because if there are other molecules hanging around in there, when our particles go down, they smash into them and the experiment doesn't work. And so vacuum is very important for us. It's got to be really, very good. So our particles go whizzing down the accelerator. That's it. I'd like to play you a little animation, which I hope will show you a little bit more of what happens. Later I'll play you an animation and show you what happens. First I'll do a little thing here. This is a thing you've probably all seen, but I thought it'd be useful to remind you. Here is the classic structure of an atom of which everything is made. That we have the nucleus. Inside the nucleus there are other particles known as protons and neutrons. And inside the protons and neutrons there are little particles called quarks, which, remember that word, you'll hear it later on, quarks. But here at SLAC we really are interested in these ones here, the electrons. The electrons are the tiny, tiny particles that whiz around the outside of the nucleus in the atom. They're so small they really have no dimension. Again, it's one of these things that goes beyond our sensitivities. They have no dimensions really, but we can collide them together. I don't quite understand that. Here we go. So we're talking about electrons. Let's see if I can get this. So, excuse me. That's better.
Well, you know, it really can't be a little sphere like that because they're away from it. I know that. So you might want to call it a quantum mechanical particle.
Yes.
You're going to call it a particle.
Right.
It isn't like this.
you're quite right, and throughout my talk I will take big liberties with things. But at the end of the talk we'll have a long time possibility of discussing more precise definitions of some of these things, whether wave functions or particles. And in fact, at this time, I'll take the opportunity to say that at the end of the talk, outside there will be refreshments and biscuits, and there will in fact be lots of physicists out there wearing special shirts, and so you can go up there. Though you could probably recognize them without the shirts. Sorry. And they will be able to answer in detail any particular concerns that you have. Let's go back to the film. This is an animation of what's actually happening inside our linear accelerator. Here is our copper tube, and these two spheres of light represent the particles themselves. And this blue object here, in fact, represents the accelerating function, which I'll come back to at the end. So you can see here that the particles go down the linear accelerator, enter the two arcs, and then turn around the ring. And here you can see the area where they actually collide. This object here is what we call, well, we call it several things. We call it an experiment, and we also call it a detector. And it is inside this detector that our particles collide. Different parts of the detector, and there is our collision. This is running backwards. And you can see the overall geography of our lab. Here is the linear collider and the arcs of the accelerator meeting up at the detector. Just play that again. So, accelerator tube, inside particles, and this is the accelerating function. Down the tube, around the two arcs, round and round, to the detector. And here we have the collision, and new particles are produced inside the detector, which we then study. This is either a physicist who should be here at work who's having more fun, or it's what we think about most of the time, but in actual fact does have some relevance to what we do here at SLAC. Because the question is, how do we actually accelerate these particles? And what is happening here with the surfer is, in fact, quite similar to what happens to our particles in the accelerator. Now, I have to say, I have never been surfing, so correct me if I get this wrong, but it seems fairly logical. Here you are, you're sitting on the ocean, on your surfboard, you're basically stable, you have no energy. Coming roaring up behind you is this massive wave, and you get onto that wave, and suddenly you've got a lot of energy. You are absorbing the energy of the wave, you're being pushed forward by this colossal force which comes into you and enables you, in fact, to do all kinds of cool things with energy that you simply didn't have at rest, that you absorb the power, the energy from the wave. In our accelerator, we do exactly the same thing. We have our little electron, and we have a wave function, which in this case are radio frequency waves. These are generated by equipment here at SLAC, pushed into the accelerator, and our particle, much like the surfer, this comes up behind him, the particle hops onto the wave and absorbs the energy from the wave and is pushed along, constantly gaining more and more energy from its contact with the wave. So surfing and particle physics are essentially the same thing. Now, here's another thing which is something to do with particle physics. I've only been in America for 2 years, but I must say I've drunk more coffee since I've been in America than I've ever in my life. big cups of coffee, and I think it's fantastic that, I'm feeling pretty slow and dreary, and I have a big cup of coffee, and it really perks me up. I get very energetic. I feel a different person altogether. And in some ways, what we do in our accelerator is like taking a big dose of coffee, because the word accelerator is in fact a pretty poor word to describe what happens here in our machine. Accelerator gives the idea that you're actually making something go faster. This is not necessarily the case here, that by the time our particles have gone about 10, 15 yards down the accelerator, down the 2 miles, they are already traveling more or less at their maximum speed. They really don't get very, very much faster. They're going at 99.9999999, you've heard it before, of the speed of light. They don't get very much faster. But what we do in the accelerator is, in fact, pump them full of energy. They're going down the 2 miles, and all the way down, it's like stopping a coffee shop, and they get another dose of coffee, which makes them incredibly energetic. And we don't just give them 1 cup of coffee, we give them loads and loads and loads and loads and loads of coffee. By the time they've absorbed all this, they are really very buzzed. And things get much worse, because we then give them pots and pots and pots and pots and pots and pots of coffee. And so by the time they get to the end of the accelerator and they're going around the arcs, they are really very, very, very hyped up particles. They are full of energy, which we have injected into them by this wave function that I was explaining before, that they're being surfed along, pumped, all this time full of energy. And so they're very different creatures at the end than when they reached the collision point than they were when they started. In fact, I think it's rather a sad story. Occasionally I worry about it, that you get a poor, innocent little electron who's minding his own business, and you throw him down this accelerator, pump him full of coffee and energy. He's got no control, because an electron has a negative charge. And so if you put a positive charge in front of him, poor thing is automatically attracted to that positive charge. And so we have total control over these things. So they have no free will. They go down the accelerator, they're pumped full of this energizing process, and then they collide with something else and are smashed into out of existence. A pretty poor and sad life for an electron. So, but nobody's started up an electron protection society quite yet, please. Anyway, I've talked for long enough. As we're in America, we'll now have a commercial break. So you can not go out and get popcorn and drinks, but I'd like to do a commercial. This is a commercial for Stanford University. That here at SLAC we have a unique position, of which is a tremendous privilege for us, is that we are part of, an essential part of, a world-famous research university. That we benefit enormously by the proximity of Stanford, where there's this tremendous tradition of high-class research, and I believe Stanford benefits from our proximity, being one of the great fundamental research laboratories of the world. It also gives us a slightly different status from most big research labs, which are government-run, not necessarily very attached to academia. It gives SLAC a particularity amongst the research labs of the world. And I'm delighted to work for Stanford. My mother has never taken me seriously, but when I said I was going to work at Stanford, at last she seemed to be pleased with me, so thank you very much. My mummy likes it. Let's go back. Who is the most famous physicist in the history of... Newton. Galileo. No, it's Einstein. Here he is, Albert Einstein. Albert Einstein, it's very interesting. He was elected, I think Time magazine elected him as the personality of the 20th century. I know, speaking to Science magazine editors, they say each time they put Einstein on the front cover of a magazine, the sales go up by 10% automatically. He has had an emblematic influence on our period. And here at SLAC, his work is an underpinning of a lot of the stuff we do. If you buy an Einstein t-shirt, what is written on the front of it? E equals mc squared. You're right. It's quite right. In fact, Einstein himself had... He started the trend. He gets a percentage. E equals mc squared. Legendary, mythical formula. What does it mean, E mc squared? Well, my understanding of it is E stands for energy. M here stands for mass. And c squared is something mathematical which we don't care about, forget about. Let's just call it E equals m. Energy equals mass. But what Einstein put down very, very clearly is that there is a total equivalence between energy and mass. And in some ways this is very obvious, that we see this all the time. You get a lump of wood, you burn it, its mass, the mass disappears, its mass turns into energy. And this is the way we usually see it. We see mass turning into energy, oil turning into hundreds of miles down the motorway. We see coal turning into heat. E equals mc squared. But here, it's rather different. Because what we do here at SLAC is, in fact, we get energy and we turn it into mass. That people talk very frequently about atom smashers, that accelerators and atom smashers go together. The idea that we get atoms or particles together and smash them up to see what's going on inside. It's not really like that. It's something much more subtle and more beautiful, I think, that goes on here. That we get our particles. As I say, we pump lots and lots of energy into them. They have loads of coffee. They're very, very energetic. They come together into a collision. And in this collision, and remember they're traveling at the speed of light, in this collision, they are completely annihilated. They don't break up into little bits. They are totally and utterly annihilated. And all the energy of the speed and all the energy they've been given by our accelerator is concentrated for a very short period of time in an incredible density of energy. Energy. Energy equals m. Energy equals mass. And what happens is, from that energy is created new mass. This new mass is shown, in fact, in new particles. And this is always at the very basis of what goes on in our particle physics experiments. Particles collide. In their collision, they create very, very dense conditions of energy. And from that energy, magically appear new particles. The particles that go in are not necessarily the particles that go out. I've tried to represent this here in a sort of way which maybe makes it a bit easier to understand. We'll see what happens here. This is at the heart of all particle physics here at SLAC. We'll look at it again. So here we've got a candy bar traveling along at the speed of light with enormous energy. Here's an anti-candy bar. They collide, and pure energy is formed. And from that energy comes out new candy. All kinds of different candy from the candy that went in. That here you can see, well, we'll see later on. Just watch it again. Collision. And out of it, we get all kinds of new stuff. We get gummy bears and lollipops and M&Ms. That if you get something, well, our particles traveling at the speed of light create energy, and out of this energy comes new mass, new particles. Indeed, in particle physics, that we know the masses of the particles. And in fact, we can create our particles more or less at will, because energy and mass is the same thing. If we create the energy conditions which is the same as the mass of the particle, then out comes the particle we're looking for. We can tune our accelerator to create the particles which we want to study. So if in this case we were particularly interested in M&Ms, for example, we could tune the energy of the particles which collide so that out comes M&Ms, which we can then study at our own leisure, that we can create the conditions to produce the particles we want to do. So some people may be particularly interested in gummy bears, therefore we change the energy of our accelerator to produce each time in these collisions gummy bears and anti-gummy bears. In actual fact, in this case, it looks like. Same thing. Excuse me, I'll just, here we have lollipops. I think you get the idea that at the heart of our collisions is this process, which is collision, create energy, out of the energy, new mass. Sorry, somebody asked the question there.
I was asking, how do you isolate positron and electrons in this question?
Right. Something I'll go back on a little bit. Good question. A positron is antimatter. Antimatter and matter do not like each other. In fact, they really don't get on at all. When matter and antimatter meet, they fight and destroy each other. And therefore, dealing with antimatter is a very difficult and complex problem for us, because if the positrons, which are the antimatter particles, touch in any way at all any matter, i.e. the side of the accelerator or any other molecules hanging around, then they annihilate and disappear, and we can't have our collision. So the answer to your question is, with incredibly complex and wonderfully effective technology, we can isolate the antimatter, the positrons, in an electric field, magnetic field, so that they are trapped in this field, kept on exactly the trajectory we want them to follow, until they meet the electrons to create this collision. So, go back one. How did the universe begin? We've had a hint. The universe started with the Big Bang, or lollipops. The Big Bang. Big Bang, huge concentration of energy some 12 billion years ago. Our understanding is that the process of the Big Bang, therefore the creation of our entire universe, was very similar to what I've just described in our particle collisions. But the Big Bang was a concentration of energy from which matter was produced. Indeed, lots of matter, lots of mass, indeed, all our universe. And what we are reproducing in our collisions here, in the particle accelerator and detectors, are the conditions that existed very, very, very close to the Big Bang. That when our particles collide, they are recreating the conditions that we believe existed 1/1,000,000th of a second after the Big Bang. So we are able to recreate the conditions of the very, very early universe and study how the universe evolved from that state into the state it is at now. And the study of the Big Bang and immediately after the Big Bang is one of our main jobs here. And given the movie with a Big Bang concentration of energy, creating out new matter, and you can see that matter here is not just little particles, but in fact the galaxies, the planets which make up our universe, which were created in a very similar way to the physics that we do here. Back to our overview of SLAC, you can see here the 2-mile-long accelerator and the ring. I'd like to concentrate now a little bit on what happens here where the collision takes place, which is our main particle physics experiment. I'd like to show you what is actually inside the arcs of this ring. What is inside is this. We can see a tunnel inside which there are 2 separate beam lines that in here, if I can actually touch it. In here is a perfect vacuum, and I think there's electrons going down this way. Perhaps Jonathan, correct me. Electrons going this way. On the top beam line, you can see a separate tube down which are traveling the positrons. They're going in the opposite directions around this ring. Here we can see magnets, which are placed to keep the electrons and positrons on exactly the right track. And finally, after the acceleration, the particles collide together inside this huge piece of equipment, which is called the Babar experiment. Babar is a very large international collaboration of physicists. There are now something like 600 physicists working on Babar. These physicists come from all over the world. I think there's now 10 countries who actually actively participate in this experiment. Babar comes from physics hit talk, cool language. We always study in Babar are particles called B particles. And we study B particles and the antimatter B, which is called, the antimatter version of the B. How we write this is B bar. We put a minus above the B, so we get B bar, B bar, 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 bar. And this is the name of the experiment. It's also named after an elephant, which you probably know better. Babar has been a most incredibly successful experiment here. It's been running now since '99, and it's made enormous progress in the understanding of one essential mystery. That in the Big Bang, physics tells us that exactly the same quantities of matter and antimatter should have been produced during the Big Bang. Now, as I've already explained, that matter and antimatter do not like each other. In fact, they get on so badly that they annihilate completely on contact. Therefore, same quantities of matter, same quantities of antimatter. Immediately after the Big Bang, cosmic battle, cataclysm, where, in theory, all the matter annihilates all the antimatter, leaving no matter at all. This is what the laws of physics suggest. However, there's something patently wrong with all of that, because here we are. We live in a matter universe. There's lots and lots of matter around. And the big question which we're asking is, what was the effect, what happened at those very, very early moments of the universe, which allowed matter to become dominant and therefore allowed the universe to exist? Babar did fantastic measurements, which were published first in 2001, which showed the slight difference between matter and antimatter, which goes a long way to help to explain this, though not a full explanation. And indeed, last year, about this time last year, a completely new particle was discovered here at SLAC, which was not expected. It was a rebel particle which caused a big stir. And that in turn has created a whole new branch of study in particle physics. And so in fact this year, Science magazine put it through as one of the big breakthroughs which they were expecting to see this year in science. That B factories is another name for what we do here. Produce particles containing heavy bottom quark, which has been hinting at physics beyond the standard model. Physics community abuzz with the factories, one in California, which is us here at SLAC, and our colleagues in KEK in Japan. So we're at the moment at a very, very exciting time in particle physics with this study of the matter-antimatter asymmetry and strange new particles that are coming out of it. Commercial break. What's next? A measure from our sponsors, I think, is what it is. The Office of Science. Where does the money come from to do all of this? We get the vast, vast majority of our financing from the Department of Energy. The Department of Energy, a particular office which is called the Office of Science. So 90% of our funding comes from them. I would like to say thank you very much. And in fact, thank you very much, Office of Science. Thank you all very much, because it's your taxes that go towards paying for this. if you meet anybody from the Office of Science or the DOE as you go around your lives, please go and shake them by the hand and say, thank you very much, because they do a fantastic job in funding fundamental research in America. We get other small amounts of funding from Stanford University, from the National Science Foundation, and also from the National Institutes of Health for other research we do, but it's essentially Office of Science who pay for all this wonderful work that's been done here. Pilgrimage. Do you recognize that? You can see here the 2-mile-long particle accelerator, the linear accelerator, and this is an area which we call the research yard, which is at the end. And this is where the first experiments took place here at SLAC. And the history of SLAC, the contribution of SLAC to our current understanding of particle physics has been colossal. That here at SLAC have been the big innovations, the big step forwards, the big breakthroughs in our current understanding of particle physics. This area here, with this building, which is called End Station A, and a small accelerator over here, discoveries were made here which have changed virtually everything in our understanding of particles and forces. In fact, this area here, 5 individual scientists have won Nobel Prizes from the work they've done here, which I guess makes this the most Nobel-dense area in America, which I guess makes it the most Nobel-dense area in the world, and therefore the most dense Nobel area in the entire universe is right here at SLAC, which I think we should try and get that in the Guinness Book of Records as well. The work was done here was originally the electrons came down the accelerator, were diverted into this hall here, and crashed into targets. And by watching the results of these collisions, for the very first time, quarks were analyzed, were isolated. Quarks were discovered here at SLAC. And this in itself made an enormous change to the understanding of the worlds of particles. So first quarks here. A few years later, another discovery was made at the accelerator just beside, which showed there were more sorts of quarks than that were originally anticipated. And then a few years later, another particle was discovered, which again completely baffled the current theories. Now, here's Pisa. In the history of science, there are places which have magical significance. For example, Pisa in Italy. Here is Pisa. This is where Galileo came from and started his experiments. He used to drop things off the Leaning Tower, which was a wonderful piece of experimental equipment in those days. Pisa is marked on the stone of the history of science. There is also, with Newton, Cambridge is remembered as one of the great centers. And I believe that, well, I hope that in another few hundred years, the great words Menlo Park will be also carved on the stone of great geographical places with the work that has been done here at SLAC. Just to explain a bit more about this. Here we see a block which represent particles. Don't worry. First, ignore all of these ones. Let's just look at these ones here. The ones in pink are quarks. This one here and this one here were discovered here at SLAC, the first quarks ever. And that was pretty good because it seemed that all the matter we knew was made up of a combination of this quark, a neutrino, and our friend the electron. And we had quite a simple model of what matter was made out of. Mix those lot together, it made all matter. Then came the November Revolution, as it was called, in November '74. Bert Richter, who was an ex-director of the lab and still works here, discovered a particle which proved the existence of this quark here. This was completely unexpected. Nobody ordered it. And in fact, this showed that there was another whole group of particles, a second generation of particles that existed. This again was complete innovation. Innovation here, innovation here. Quite soon afterwards, Martin Pearl discovered this particle here, the tau, which indicated, again, that there weren't just two families of particles, there were indeed 3 families of particles. The same format, 2 quarks, an electron, a neutrino, and an electron sort of thing, but 3 distinct families of particles, which is where it stands at the moment. There are 3 families of particles. Why there are 3 families of particles, we don't know. Just take it for granted that there are 3 families. And for each of these discoveries, Nobel Prizes were awarded. So, of the 12 particles which we now know to make up all the matter, 1, 2, 3, 4 were discovered here at SLAC. And I would say the 4 best ones were discovered here at SLAC. Some pictures of the people who discovered them. This is Dick Taylor, who, back with 2 colleagues, discovered the quarks, Nobel Prize. This is Bert Richter, who's trying to get out of an aquarium, I think, in that particular one. Nobel Prize, who discovered the charm quark, and Marty Pearl, who discovered the tau, which led to the 3rd family of particles being isolated. Great photo. Here we go, commercial break. What's it for this time? Let's see. Great, this is information for you. We would very much like you, if you're interested in what's happening here at SLAC, to join up our very exclusive club, which is called SLAC Connections. You can join this online by going to this address, and in fact all the machines, the computers outside are on this page. All we need is your email, and if you're interested, we will send you a monthly email letter saying what tours are available, what lectures are going on, all the possibilities that you can take advantage of to participate in the extremely rich life of our laboratory. So, sign up, doesn't cost anything, and if you get a special introductory offer, which is tours for members only around the lab. I'm now going to move away from particle physics and talk a little bit about synchrotron radiation physics, which is done here, which is another branch of our research. I don't know if you recognize this building here. This is the end station A, where the quarks were discovered inside here. And you can see from this aerial view the outline of a small circular accelerator. This accelerator is called SPEAR, which stands for Stanford Positron Electron Asymmetric Ring. Physicists are good at some things, but not making up names. This is why we use acronyms. SPEAR. SPEAR was the accelerator which was used by Bert Richter, by Martin Pearl to make these big discoveries. But also, at more or less the same time it started up, something else was noticed very much at SPEAR. When you get electrons and you make them go around corners, around a bend, they really don't like it. It makes them unhappy. And they express their unhappiness, their discontent, by in fact losing energy. When they go around the corners, they actually lose energy in a straight line. It's a bit like a big truck going around a bend. It doesn't like going around the bend. You have to slow down, you have to force it around. It loses energy going around. And so, as the electrons went around here, energy was shot off on the bends. However, it was seen that this energy was shot off in the form of very, very brilliant, very, very short wavelength X-rays. And it was realized that these X-rays could be put to work. What was in fact a problem for the particle physicists who wanted to keep all the energy inside the ring turned out to be a positive boon for the synchrotron radiation research community, which didn't really exist in those days because the first ever experimental synchrotron radiation lab was, of course, here at SLAC. That in 1974, the first people came, studies of synchrotron radiation here, which again reinforced the incredible innovation that has taken place at this lab. This has been continuing since then, and we now have SSRL, another acronym which stands for Stanford Synchrotron Radiation Laboratory. We were delighted just this January, just a month ago, to dedicate a brand new accelerator using the same structure, the same ring, but we installed a completely new accelerator for generating X-rays. This new facility puts us at an equal level of any lab in the world in synchrotron radiation research. Is that me, or is that something outside? Can you hear me? Air conditioning. Okay. The study of synchrotron, studying matter, studying structures using the synchrotron radiation has been an enormous hit. Since '74, when the first user facility started up here, there's been an explosion of the number of laboratories doing this research. There are now over 50 in the world carrying out synchrotron radiation research. As I said, we are at the moment certainly one of the equals of any of the best laboratories in the world, but very soon, if all goes well, if the funding continues, therefore be nice to people from the Office of Science if you see them, that we hope to get the funding to build a completely new machine, which is called the LCOS, Linac Coherent Light Source, which we would hope will be finished in 2008. It will use our long-suffering and very, very noble linear accelerator, and we will build some new experimental areas here. And this machine will produce X-rays with a brilliance and intensity which is way, way, way beyond anything that can be done at the moment. It is orders of magnitude more powerful. This machine is called an X-ray free electron laser. Once again, the first one in the world will be, of course, here at SLAC. Again, starting off a whole new field of research. What do these things do? What are they for? Well, I'll just give you one example. I don't want to talk too much about it because the next lecture is going to be all about it, and someone much better than me will be able to explain what we do. Old people break their bones, hips especially, fall down, snap. Why is this? That this phenomenon was so frequent, there had to be a reason behind it. With the very powerful, very precise X-rays from our installation here, we were able to look inside bone structures and to notice that, in fact, with a loss of estrogen, that the inside structure of the bone disappeared very, very rapidly, making it very weak and therefore snapping. But with an augmentation of the estrogen, this bone structure could, in fact, be strengthened. An understanding of how to stop these major fractures in elderly people came directly from the sort of research that we did, well, from research that was done here at SLAC. We also do research in drug design. Using these X-rays, we can see exactly how viruses attack cell structures, and therefore we can build barriers in the place where this attack takes place. We also do work on material sciences, computer chips now. The silicon which is used has to be amazingly pure. If there are any impurities in the computer chips, then the chips will not function. And we can see all the impurities, even on an atomic level. Kavli Institute for Particle Astrophysics and Cosmology, another branch of research that we do here at SLAC, is indeed in astrophysics and cosmology. We have a completely different view now of you have a very different view of what I'm saying here. So let's hope that this is going to work. No. Excuse me a moment. Ah, there you are, I fixed it. Don't clap. Must have something to do with vibration. Here we are, Astrophysics and Cosmology. This is a new institute which has been set up here at SLAC, a gift from Mr. Fred Kavli, who's been able to allow us to build this new institute. A new building is going to be built just right out in front here. This is an artist's impression. This is San Francisco on fire in the background. Things are changing. In the last few years, we are living a revolution in the world of physics. That new results, new findings that have been coming down from cosmology studies have shown us that all the matter we have been studying, all the physics which we have been very beautifully understanding here at SLAC and at other laboratories around the world, in actual fact only represents 5% of the matter of the universe. The visible matter is only 5%. 95% of the mass of the universe is made up of stuff which we just don't know what it is. We call it dark matter and dark energy. This is something completely outstanding and a wonderful, wonderful challenge to physicists. And the Kavli Institute here at SLAC will be working on these cosmological questions. Another big challenge for us is that it would appear that, given the theoretical models that would appear to work to explain dark matter, dark energy, we have to have extra dimensions. We've had 3, we've triangulated with 3 since the beginning of civilization, maybe 4 with time. It would appear there are 7 more dimensions working at very, very tiny levels which go into controlling our universe. These are discoveries which will be made, hopefully, within the very near future. Dark energy, Big Bang model, explosion, the universe expanding, eventually slowing down as it expands. This is what was believed until really 4 or 5 years ago. But now it's quite clear something else is happening. There's something out there called dark energy, which in fact is making the universe expand. Its acceleration is expanding, not slowing down. Completely different concepts which have been brought into the arena of particle physics. From our knowledge of the particles, the forces which have been built up here over the last 30 years, we are now in a position to go out and work with cosmologists to try and find answers to these extraordinary questions. Another project we have here at SLAC is to build a space-based telescope. We build a detector which goes onto this satellite. It's called GLAST, which is Large Area Space Telescope, G. Gamma ray, thank you, John. Gamma ray Large Area Space Telescope. This again shows how SLAC is evolving from purely particle physics, synchrotron radiation physics, now into cosmology and space-based science. Another commercial break. This time it's for tours. We run here a whole range of tours. We really want you to come and look at this stuff. You can hear about it, but I believe you me, nothing beats actually coming and looking at it. Come here, walk around a real particle accelerator, touch a particle detector, see physicists at work. Nice. Come prepared. We are delighted to get as many people around here as we can. We run set dates of tours, they are here, but we can organize tours for any group, any schools, any group of people that would like to come around, individuals. Here is a website, here is a telephone number. Contact us and we'll show you around. This is a bucket of water. Bucket of water is a good thing. You can carry water on in it. It's fine. It's a good tool. Imagine there's a little hole in it. A little bit of water comes out. Do we mind? Well, a little bit, but not really. It still carries around a lot of water in it. It's doing a good job, and we can live with that. But what happens if this bucket of water suddenly gets loads and loads of holes in it, and all the water pours out really quickly? The more you pour in, the more that comes out. This then no longer becomes a useful tool. And why I'm saying this is to try and explain how wonderful linear colliders are. Do you remember me saying that with the circular colliders, that as the particles go around the circles, a lot of energy is lost on these bends. They don't like going around the corners. A lot of the big particle accelerators in the world are big circular particle accelerators. The higher the energy of the particles in the accelerators, the more they lose as they go around the corners. And we've got to a stage with our big circular particle accelerators where the bucket's just got too many holes in it. The more energy we push in, the more is lost, and it's no longer a useful tool. So, the next accelerator which the world's physicists want to build is a linear accelerator, but a very, very long linear accelerator. This is a machine which will be some 20 miles long. 10 miles in this direction, particles are accelerated to the detector in the middle, the other particles coming 10 miles down to collide. SLAC is playing a really major role in the development of this next linear collider. We have the experience. We have a linear collider. Other labs don't. And a large part of the activity at the lab at the moment is research and development on this huge linear collider. This linear collider has been defined by all the areas in the world, all the physics communities, as the next big project in physics. The Asians, the Europeans, the Americans all agree this is the next big project. We have to decide where it's going to be built and exactly what technologies are going to be used, and indeed who's going to pay for it. So once again, if you see people from the Office of Science, you shake their hands that we need their money. But here's a sketch of a possible design of this new machine, which appears to be in some lovely Californian setting, and we'll keep our fingers crossed for this. But this is the way to go. This is the future which SLAC will be very much involved in. As I said, this is an international project that no one nation, no one area can either afford to pay for these big pieces of equipment or indeed have the brain power, the experience to build it on their own. The most efficient model is international collaboration. Here at SLAC, we already have this. This is an American laboratory, but it is also a highly international community here, that our staff, our really remarkable staff, are very international. I'd like to show you a film which we made just recently. Uh-oh. What do you think?
Hi, my name is Marcella Bona. I work here at SLAC as a physicist. I'm Italian. Vengo da Torino, che è una città nel nord-ovest d'Italia.
Hi, my name is Patrick Mugli. I'm here at SLAC to do some experiments. Originally, I'm from Switzerland. La Suisse, c'est le plus beau pays du monde.
Hi, I'm Hassan Jawahiri. I'm from University of Maryland doing research on Babar at SLAC. I'm originally from Iran.
Hi, my name is Ray Cowan. I work here at SLAC. I'm from Chattanooga, Tennessee.
Hi, my name is Jing Zhang. I'm originally from China. I work at SLAC. 大家好，恭喜发财。
Hi, my name is Ardemaz. I'm working here at SLAC in E164 experiment. I'm from Turkey. Herkese Antalya, Türkiye'den selamlar.
Hi, my name is Wouter Hulsbergen. I work at SLAC. I come from the Netherlands. Ik ben geboren in Gouda en daar wonen allemaal kaaskoppen.
Hi, I'm Olga Yakovleva. I work here at SLAC, but originally I'm from Russia. Привет всем россиянам.
Hi, I'm Chris Cormack. I'm from the University of London, but I currently work at SLAC.
Hi, my name is Julie, and I'm working at SLAC as a PhD student. I come from Paris.
Hi, I'm Stephen Gowdy. I'm working at SLAC on Babar, and I'm originally from Glasgow in Scotland.
Hi, my name is Vitaly. I came from Russia, from Moscow. I work here in SLAC.
Hi, my name is Devin Johnson. I work here at SLAC on the E164 experiment, and I'm from the Midwest of the United States, Minneapolis, Minnesota.
Hi, my name is Tatsumi Koi. I'm working here at SLAC and come from Japan. はじめまして、小井辰巳です。日本から来ました。ここはとても暮らしやすいところで気に入っています。
Hi, my name's Catherine Schofield. I'm working out here at SLAC, but actually I'm from Liverpool in England.
Hello, I'm Max Bach. I work at SLAC, and I'm from the Netherlands.
My name is Eli Rosenberg. I do research at SLAC. I come from Iowa State University in Ames, Iowa.
Hi, my name is Sandrine Emery. I'm working on the Babar experiment at SLAC, but d'origine, je suis française et je viens de Saclay.
Hi, I'm Gabriele Simi. I work here at SLAC. I'm originally from Italy. Venite a visitare l'Italia.
Hi, my name is Gagan Mohanty. I'm working at SLAC, but originally I'm from India, and it's great to be here. Shukriya, dhanyavad, namaskar.
Hi everybody, my name is Carl Anderson and I'm working here at SLAC, but originally I'm from Sweden. Och det är otroligt roligt att jobba på SLAC.
Hello, my name is Liliana Teodorescu and I'm from Romania. Sunt din București și mă bucur să lucrez în California.
My name is Keelan O'Connell. I work here at SLAC and I'm representing the California contingent. I'm originally from Los Angeles, California.
Good day. My name is Patrick Krejcek and I'm an accelerator physicist here at SLAC on the 2-mile linear accelerator. Cheers, mate.
Hi, my name is Moshumi. I'm from Bangladesh. I work at SLAC.
Hello, my name is Leif Wilden. I work here at SLAC, but I come from Germany. Und ich schicke einen schönen Gruß in meine Heimatstadt Hamburg. Tschüss.
My name's Leija. I'm from China and I'm working at SLAC.
Hi, my name is Abi Sofer. I'm working here at SLAC and I'm from Israel. Shalom l'kulam b'Israel.
Hi, I'm Eduardo Couto Silva and I work at SLAC and I'm from Brazil. You know, the place where we win the World Cups.
Hi, my name's Neil Calder. I work here at SLAC, but originally I'm from Bonnie, Scotland.
Hi, my name is Marcella Bona. I work here at SLAC. Italian. My name is Marcella Bona.
I'm from Bonnie, Scotland. And it's great to be here. Shukriya, dhanyavad, namaskar.
Thank you. This film just goes to show that this is a truly international place to work. It's a great pleasure to work here because if you want to see how international collaboration can work and how effective it is, come and spend a few days here at SLAC. Quickly, a photo, SLAC innovation. These guys here, it's a very poignant photo for me. The guy in the middle is Tim Berners-Lee. He invented the World Wide Web. He was at CERN at the time. I was at CERN. I was in charge of communication. He came to my office and said, Neil, I think I've invented something useful. I said, oh yeah, what's that? He told me, and I didn't understand, and I didn't put a patent on it, and I didn't make the billions of dollars which I could have done. It's always been hard for me, this. Tim invented it at CERN. We didn't do anything. It took Paul Kuntz from SLAC, again, he had the innovation, the lightness on the feet. He came to CERN, he understood what the web was, came back here, and created the first website in the entire United States. He put a very useful database onto this website. Within weeks, thousands of people were using it. Websites grew up all over America, and it is what it is today. That the World Wide Web, the internet explosion, came into America, or say, went into America through the gates of SLAC. Again, innovation. The guy on the right, Bibo, he wrote the first ever book, the sort of seminal work on how to write HTML, and again had an enormous influence on the progress of the internet revolution. And we continue to have an influence on computer technology. This was last year. We broke the world internet speed record. We can see then we could send 2 DVDs across the world in less than a minute. That's nothing. Now we've broken it about 4 times since, and I think it's something like 15 DVD across the world in a minute. Okay, this is research still, but in 10, 15 years, these sort of bandwidths, this speed of transfer of information will be common to all of us. And the groundbreaking research is being done at labs like SLAC. As we get to the end, we get more commercial breaks. And this is coming soon, the next coming attraction to this auditorium. These are the public lectures which will take place over the next rest of this year. Synchrotron radiation, the light fantastic, our lopsided universe, matter and antimatter, metals, molecules, life and death. This is a philosophical talk, it sounds like to me. Partial astrophysics, from compass to modern technology. Don't miss any of these talks. They will all be fascinating, more in-depth talks on the work here at SLAC. In conclusion, here at SLAC, science never stands still. Science is constantly evolving. There are constantly new challenges for the world of physics. But at SLAC, we have been able, throughout the life of the laboratory, to lead the innovation in so many ways. Innovation in particle physics, innovation in synchrotron radiation research, innovation in computing. We have now a wonderful toolkit at this university to answer the big questions of physics. Our particle physics machine with Babar is pumping out wonderful research. The synchrotron radiation side is very strong and will get stronger. With particle astrophysics, we are one of the first places in the world to have an institute which is directly studying the new questions posed by a better understanding of our cosmos. We have an exceptional staff. The staff that run the laboratory and all the users that come from all around the world to do research here. And we are entering here at SLAC into an incredible era of discovery. So watch this space and you'll be hearing more about us, I hope. Thank you very much. Thank you very much for that acknowledgement. Originally, I was going to say there would be questions, but I have gone over my time. I'm sorry. However, for all those who would like to ask questions, as I've said, there'll be real physicists out there wearing special clothes so you can recognize them. There are also biscuits and drinks. So I suggest now you go out there, you sign on to our special club and talk to the physicists. Thank you.